Hi, I'm Maxim Wolf from the University of Wuppertal, and today I wanted to present the paper White Noise Windows, a new data augmentation technique for time series. Now I'm switching to the presentation. Okay, as I mentioned, the name of the paper is White Noise Windows, data augmentation for time series, and I wrote this paper with my co-authors Philipp Houston, Nicola Numerical, Fasin Gorban, and Anton Kummert, all from the University of Wuppertal. I want to start with a short structure of this presentation. We start with the introduction. Afterwards, we go into the functionality of white noise windows. Then we go into the datasets used for evaluation. Then we come to the method and implementation before we discuss the evaluation results. And then we go into a short conclusion. So, data augmentation is used to increase the samples number in the data sets by generating synthetic samples, and has the goal to increase the generation capability of classifiers. For the most machine learning tasks, a larger data set can improve the model performance. However, for many applications, especially in industry, only small data sets are available, and for this reason, data augmentation has become an important field of research in machine learning in the recent years. So there are many application areas of data augmentation, such as compensate for class imbalances. Here, by augmenting the underrepresented class with synthetic samples, a classification bias towards a larger technique can be avoided. There are many different fields where you can use data augmentation, particularly in the field of image processing, but also speech recognition. There are many well-proven data augmentation methods. In image processing, for example, new samples can be generated by simply rotating or flipping the image without losing information or much information. And in the field of speech recognition, you can compress or stretch the sample slightly, which corresponds to slowing down or speeding up a speech to obtain new training data samples. So, but also in the field of time series classification, there are several different data augmentation methods, like the weighted dynamic time warping as an example. And in this paper, we want to present a new technique for data augmentation that we call white noise windows. How does it work, the white noise windows? White noise windows is a simple method to augment time series data sets. If you have a training data set, we first normalize each time series in this data set, and then we multiply to any number n of identical time series, so that the augmenting data set becomes, if you choose the multiplication number n as 2, the n manifold, the 2 manifold of the original training data set. And finally, a random part of each time series in the augmenting training data set is replaced by white noise. The window size of the noise is a hyperparameter in this case. And in our evaluation, we examine a window size of 5%, 10%, or 20%. Here you can see the functionality of white noise windows. You have original training data samples. We in this case we choose n as 3. We made 4 times the original training sample, but in the augmented time series we enrich with noise. Here you can see 5% noise, here you can see 10% noise, and here you can see a time series with enriched 20% noise. So to prepare the evaluation, we have selected 9 data sets from the UC and time series classification archive and prepared them according to a scheme. So, like I mentioned, we first normalize all time series in the training data in the first step, and to values between 0 and 1. And next, we continue working with the training data and generate additional n-1 identical time series from each time series in the examined data set. So we then replace a random part of each time series with noise, as you can see here. And So we end up, we choose the parameters as n/2, n/5, and n/10. So we end up with 2 times, 5 times, or 10 times the data set. That's how our method works. We examined it on 9 data sets, as I mentioned, all from the UCR time series classification archive. The UCR archive categorized the data set according to different types. We are focused on the types ECG, sensor, and motion for the evaluation and distinguish. We tried to select data sets distinguished in number of classes, size of training data, size of test data, or sample lengths. You can see here our 9 data sets: ECG200, ECG5000, Tulip, ECG, Starlight Curve, Stony, Albert Roberts, Super Smoke Spring, Gunpoint, Inland Scan, and UFG through Library X. And you can see a difference in the number of classes. Maybe here we get in the ECG200 only 2 classes. In the UF you get 8 classes. We have different size of training data and test data sets and difference in sampling. So hopefully we get a meaningful evaluation. So as I mentioned in the first step, we normalize all time series values to 0 and 1. Next, we continue working with the training data and generate additional n-1 identical time series from each time series in the data set that we use. We then replace the random part with each time series with 5, 10, or 20% white noise. And as I said, we use n/2, n/5, and n/10 for evaluation, ends up in an augmented training data set size of many folds of 2, 5, and 10 times compared to the original training data set. So this procedure is applied to all 9 data sets that I showed before. So for each UCL data set tested, 3 augmented data sets with a multiplication number of n/2, 5, and 10 are classified using Kenya's neighbor as for n testament compared against the base results in terms of accuracy and appearance for every window size, 5%, 10%, 20%. So now we are coming to the evaluation results, and you can see that using white noise windows, significant performance improvements can be achieved for the KNN classifier. Overall, all data sets show better results using white noise windows. More specifically, white noise windows is suitable for all investigated types of time series data sets. Even for data sets with different class sizes, improvement can be shown. For example, the performance of the Sony Albert data set as well as UVA data set have been improved. You can see here, Sony Albert, we have huge improvements, but also in the U-Wave, we can examine better results. And the performance was significantly better, and we therefore recommend using white noise windows for the KNN with a window size of 5% and n/10. That shows the best results you can see here in 6 out of 9 cases. And n/2 for ECG signals can be a good choice since it gives the best results for all 3 ECG data sets. You can see it here. For the S4M, the performance can also be improved using white noise windows in 8 of 9 datasets. And for all types, improvements in degradation were recorded. It is noticeable that white noise windows tends to worsen the performance on datasets with more than 7 classes in all cases. So overall improvement was achieved in most classes. White noise windows can especially be useful for KNN classifier. Here, every batch result could be improved if parameters are well chosen. The evaluation results show also that the window size of 5 or 10% is reasonable. It is assumed that with a window size of 20%, too much important information is lost. This usage is supported by the often lower F1 score for a window size of 20%, in contrast to window size 5% and 10%. Furthermore, n should be chosen too small because with n/2, in no task the best result could be achieved. White noise windows is suitable for data with different sample lengths, classes, types, but however, white noise windows should be carefully used and the performance of the classifier needs to be closely monitored as white noise windows may have a negative influence on the performance. So as conclusion, white noise windows can help to improve the performance of classifiers and avoid overfitting. In most evaluation tasks, an improvement in accuracy and F1 was achieved. Evaluations show that especially the KNN classifier fits from white noise windows. And for parameter setting of white noise windows, it turned out that the window size of 5% or 10% combined with n/10 or n/20 N/5 or N/10 is widely recommended. It should also be noted that considerable performance deterioration can occur using white noise windows. It is therefore important to use white noise windows carefully and to monitor the development of the performance of the classifier used. So thank you very much. That was it from my side. Goodbye.
Hi everyone. Today I will be presenting the paper entitled A Semi-Adaptative Large Neighborhood Search for the Maintenance, Scheduling and Routing Problem. I have divided my talk on the following 4 points. First of all, I will introduce the problem. Then, I will present the proposed resolution method, semi-adaptative large neighborhood search. In the third point, I will present the experiment and the results obtained before concluding. Our objective, or the objective of the problem, is to determine simultaneously the optimal routing and maintenance plan, and to assign technician to maintenance operation while trying to match the arrival date of technician with the optimal maintenance time. In our problem, we place ourselves like a company which provides maintenance services that need to ensure good quality maintenance at the least overall cost. Customers are geographically distributed and have each several machines subject to random failure. Each machine requires several maintenance operations. We need then to assign technician to the maintenance operation. We have distinguished 2 main streams of research. The first one uses the routing model to plan maintenance operation, like technician routing and scheduling problem. The resolution methods that were used to solve this kind of problem are exact approach, like brush and price, programming, and local search-based method, mainly ALNS. The second stream of research combines maintenance and routing problem, like risk-driven maintenance problem. The methods used here are also based on local search, such as variable neighborhood search. Adaptive large neighborhood search is the resolution method chosen to deal with the problem. In the literature, authors generally propose specific operators, adapt existing ones, or intervene in the selection mechanism. Some literature selection mechanisms are presented here. The first one is the roulette wheel selection mechanism, introduced by Rupp and Pissinger. It is a probabilistic method where variable score SH of the heuristic are increased depending on 3 cases. The best solution is improved, the current solution is the only one improved, or the new solution does not improve the current solution, but it is accepted with a probability. Cost improvement-based adaptation, adopted by Labori and Gobart. It uses the same roulette wheel selection mechanism. The score component is, however, different. It uses the cost improvements and the sticky computational cost of the operator, time of the operator. It favors the operator which not only improve the solution like in here, but also improve it faster. The third selection mechanism is learning automata, used recently by Kota et al. It is a type of machine learning algorithm. It uses the same roulette wheel selection mechanism, but one among several actions is chosen through interaction with the environment. The formula here are different than the previous. In the problem, we minimize the total maintenance cost to obtain optimal period for each machine and frequency of maintenance operation in the horizon. We then calculate the optimal execution time, the time windows, and the operations duration that are input for our routing model. The routing model seeks to minimize the total travel cost and the penalty cost of violating the upper bound of the time window. The constraints are the following: visiting each operation once, minimizing the number of vehicles, and the lower bound of the time window is a hard constraint, where the upper bound of the time window is considered as a soft constraint. My second point concerns the resolution method. The proposed algorithm is presented here. We first initialize weight and probability of the heuristics, the temperature also, and we construct the initial solution using the best insertion heuristic. We repeat for a certain number of iterations the following. If there is no improvement, counter improvement equals 0. We select randomly the destroy and repair operator. To diversify the search, otherwise we select according to the probabilities of the past success using the roulette-width selection mechanism. This is what we call a semi-adaptative mechanism that alternates between diversification and learning. The random selection here is an opportunity for learning process to have sufficient time to learn new information from other experiments in the environment, while diversifying the search in the same time. SDR receives the destroyed and repair solution S. We apply local search to the new solution S prime, and we record the number of times we have used our destroy and repair operators. If the objective value of the new solution S prime is better than the objective value of the best solution, the best solution becomes the new solution S prime, the current solution becomes the new solution, and the score increased by a reward delta 1, and control I is set to 1 to say that there is an improvement. If the new solution improves only the current solution, the current solution becomes the new solution, and the scores are increased by an amount delta 2, which is inferior to delta 1, and we say that there is no improvement. Control I receives 0. The third case is when the new solution does not improve the current solution or the best solution, but we accept it, however, with a probability. This is the probability. If the random number is inferior to this probability, the current solution becomes the new solution S prime, and the score are increased by an amount delta 3, which is inferior to delta 2 and delta 1. We set counter I to 0 to say that there is no improvement. The temperature is decreased by a cooling factor alpha every iteration, and the weight and the probability of the heuristic are adjusted. Intensification is ensured by variable neighborhood descent that use the swap insert 2-opt étoile and 2-opt neighborhood structure, the semi-adaptative mechanism, and the repair operator, while diversification is ensured by the stimulated annealing acceptance criteria, the semi-adaptative mechanism, and the destroy operator. The destroy operator used here destroy 40% of the solution. We have used the highest cost removal that removes the task with the highest cost. The highest risk removal is a problem-specific operator that we designed for the problem. It removes the task with the highest risk of machine breakdown or probability of failure. Related removal removes the similar parts of the solution. To answer them in a better way, the lower the relatedness R, I, J, the more related the task. This operator is the one that can be more problem-specific by adding as many terms as needed. Here we have a time term and a travel time or distance term. The time-oriented removal removes tasks that are approximately served at the same time, and distance-oriented removal removes tasks that are geographically close to the chosen request. There are particular cases of related removal where time-oriented removal considers only the time part, and distance-oriented removal considers only the distance part. Repair operator or heuristic insert tasks that were destroyed. They can be exact or heuristic. Exact if the sub-problem isn't too large, and heuristic if the sub-problem is large. Here we use heuristic operator, basic greedy insertion, insert task in their best position in a greedy manner until there is no task to be inserted. Best insertion is the same, but it considers the order of insertion. To regret insertion, insert task based on the regret value instead of the cost value, which was here the least bad choice. The regret value is the difference between inserting in the best position and in its second best. Six sets derived from Solomon instance were used, and an instance inspired by a real case. We have generated maintenance parameter, and we have tested a number of operations that varies between 6 and 73. For measurement, we use the average percent decrease of objective value when using the proposed algorithm semi-ALNS compared to the comparative algorithm or the simplex solver. The average percent decrease of CPU time when using semi-ALNS compared to the comparison algorithm or simplex, and the relative percent deviation for robustness between the average solution and the minimum solution. We noted that for very small instances, which are solved in few seconds, using the solver is better. For medium-sized instance, the objective value improved slightly and the CPU time considerably. And for large instance, both the objective value and the time improved considerably. Very large instances are not solved by simplex, while ALNS returned a solution. For all instances for which we obtained a solution, the improvement of objective value is 18.26% in average, and the CPU time decreased by 62.30% in average. The figure illustrates clearly that for small and medium-sized instances, the objective value of SALNS is either smaller or the same as simplex. The time of SALNS in orange is considerably lower compared to simplex. Another comparative study has been realized to compare SALNS with classical ALNS, with and without rigid score, and learning automata ALNS with and without updating. Choose the choice of operator every period. The objective value improved slightly, 1%, and we notice that SALNS is more robust than classical ALNS algorithm and learning automata ALNS algorithm. The time average is improved by almost 20% in comparison when compared to other algorithms. We can see clearly that in the figure 2, we can see that SALNS here in blue has less CPU time compared to ALNS rigid score in orange and ALNS classical ALNS in yellow, and that's for all instances. We can say that learning automata ALNS and that SALNS in blue here is better than or have lower CPU time than learning automata ALNS in brown and learning automata ALNS with updating every period in green, and that's for all instances too. To conclude, a semi-adaptive large neighborhood search was proposed for the maintenance, scheduling, and routing problem. It is enhanced with a semi-adaptive mechanism that ensures effective mix between diversification and learning. A new removal operator based on the behavior of risk in maintenance is proposed. It is combined with several destroy and repair operators dedicated to the studied problem. SALNS outperformed the solver in both solution quality and time. And as future work, we will include learning in the local search, procedure, test a reduced sham to decrease the CPU time, and maybe solve larger instances. Thank you.
Hey everyone, my name is Abdurrahim Zannou. I am PhD student in the University Mohammed bin Abdullah Faz. I will present to you the paper that titled An Optimal Base Stations Position for the Internet of Things Devices. So in the first, I will explain the notion of the Internet of Things, then in the general the problem scenario. After that, in details the proposed solution, and to evaluate our contribution we give some results. In the finally, I conclude the proposed contribution. So what is the Internet of Things? The Internet of Things allows objects and people to be connected from any place and at any time and with anything, using a specific network or the Internet. The objective behind these concepts is to create a connected world and facilitate the life of a human being without their interactions. For more details, as we can see here, a set of devices communicate together, where the requests are sent from a node to another until the destination is not found yet, such that each node must choose only one node from its neighbors. By the same way, all these devices can participate in this communication, where a base station acts like an interface between these nodes and Internet. The IoT is characterized by constant nodes and loosey networks, where the available resources are limited and the network structure is unstable, which are often limited to power consumption, storage capacity, processing capacity, etc. So, for the problem scenario presented here, the data transmission from nodes via multiple hop communication to a base station is expensive in terms of data delay and energy of consumption. Furthermore, the nodes near to base stations will consume more energy than others. To resolve this problem, we deal with the placement of multiple base stations. The objective is to make the most of nodes connected to base stations via one-hop communication, and other nodes via an optimal path. To do this, we improved an algorithm of clustering to be suitable to our scenario to make the most of nodes connected to base stations via one hop, and a new method allows the out-clustering nodes to be connected via an optimal path. We assume that the different informations of nodes are known by an entity central, such as the coordinates of nodes, the execution time, the storage capacity, etc. It is aware of all these unvaried properties. Furthermore, the nodes are stationary, deployed in a given area. The mean shift clustering is adopted to cluster nodes. This algorithm is more suitable for the problem discussed because it has a high accuracy on a large scale, adaptable for different densities of nodes, and there is no issue of local minima. As nodes are clustered based on their locations, the base stations will be located in centers of clusters. The nodes within the cluster can communicate with their base stations via one hop. However, the nodes that exist out of clusters, named outlier nodes, cannot connect directly to base stations. The outlier nodes can be located between multiple clusters. The objective is to make the outlier nodes choose an optimal path to achieve the base station using adjacent nodes. To choose the optimal adjacent nodes to base stations, we based on a set of parameters such as cardinal of cluster, the distance of center cluster to outlier node, adjacent node distance to outlier node, adjacent node ability, and the number of related nodes for the candidate adjacent node. Then, using these properties, we calculate the pickup probability of adjacent node G, for example, for outlier node E, as noted here. The outlier nodes can choose a set of adjacent nodes as Rayleigh nodes based on the pickup probability, where the data will be transferred to the Rayleigh nodes. Furthermore, the outlier nodes that have not the adjacent nodes, the outlier nodes that choose their Rayleigh nodes will consider it as adjacent nodes. Then we apply the equation 1. To evaluate our contribution, we evaluate the clustering of mean shifts by measuring the number of base stations, also the number of nodes connected to base station via one hop and via multi-hops. The number of base stations required is 16, as shown in table 1. 96% of nodes related directly to the base station via one hop, 3% via two hops, and 1% via three hops. As a result, the accuracy of the proposed algorithm is higher. The figure 1 shows the network lifetime of the proposed approach compared with benchmark method. As illustrated, the network lifetime of our approach is increased than other method. The result is due to the mechanism of clustering such as 96% of nodes are adjacent to base stations and have the shortest distance, which the energy of consumption is decreased. Furthermore, the proposed method allows nodes to choose optimal Rayleigh nodes that lead to balance the residual energies. To measure the efficiency of our approach in terms of the data delay, figure 2 shows the nature of this parameter. As illustrated, our method has data delay from source to destination less than the benchmark method, such that our approach allows packets to come through the optimal path. The results are explained by the mechanism adopted in our approach, where the most nodes are connected via one hop with a low path distance, and the package shows the adjacent nodes that have more capacity. In this paper, we proposed a new approach that deals with the placement of base stations in a given area, where the nodes are constrained in terms of energy consumption, processing time, storage capacity. To resolve the problem related to the data transmission, we proposed an approach that constricts by the placement of base stations and a method of selecting the nodes that can be as intermediate nodes to receive the data. The simulation results show that our approach is robust with the principal issues posed by the constant nodes during the data transmission, considering the accuracy, the energy consumption, the network lifetime, and the data delay. Thank you very much for your attention.
Hello, ladies and gentlemen. I welcome you all on 7th International Conference on Optimization and Applications ICOA 2021. Today, I will be presenting my research paper on the topic predicting device availability in mobile cloud computing using conv-LSTM. Along with me, I have my collaborators which has supported me for producing this research paper. Piyush Kantidatta Pramnaik from National Institute of Technology, Durgapur, India. Nilanjan Sinha Babu from Indian Institute of Technology, Kharagpur, India. And Prasanjit Chatterjee from National Institute of Technology, Durgapur, India. So before I start presenting, let us first of all understand the outline of my presentation. My outline will be, first of all, I will be discussing abstract, then introduction, in which I will be elaborating two aspects: mobile cloud computing and resource availability problem in mobile cloud computing. Then we will have the discussion on objectives. Then I will be taking you to the deep dive into Crowdworker availability prediction, and we will be discussing test results and analysis, followed by conclusion and future work of this research paper. Now let's talk of the abstract. The quality of service of mobile cloud computing, in which the public smartphone devices are used for job execution, hampers due to users' mobility. In this paper, we propose a model to predict SMD's availability in campus-based mobile cloud computing, where generally a set of users are available for a certain period of time in a regular fashion. Predicting the user's availability before the job submission would help avoid unnecessary job offloading or job loss due to designated SMD's early departure. We recorded the real-time mobility traces of the users connected to a Wi-Fi access point of our research lab, and then we have applied conv-LSTM and another artificial intelligence technique on the mobility dataset to predict the availability of the SMD. A job submission scenario is simulated, and the extensive simulation of our approach has proved that our method has an average accuracy of 78%, making the job submission more reliable. Now let me start with the introduction. Mobile cloud computing is regarded as one of the sustainable economic alternative to the traditional high performance computing systems. In mobile cloud computing, the public's smartphone devices are used to carry out computational jobs. The mass usage of resource rich SMDs, that is smartphones and tablets, coupled with a less worrying for battery drainage thanks to energy condensed batteries and flexible charging options, mobile cloud computing has become a potential option for affordable and flexible HPCs. But one of the major issues in MCC is to handle the uncertainty of the device availability due to users' mobility. The random mobility pattern of the mobile device users, termed as crowd workers in MCC, may deteriorate the QoS of MCC significantly. So in this paper, we propose a deep learning based solution to predict the availability of the crowd workers in a campus-based MCC. And here campus-based MCC denotes that the crowd workers are connected to one or multiple particular Wi-Fi access points. And we assume that the crowd workers may connect to access points several times a day, for example, like an education institution or like a company office. So the hypothesis of our study is that we assume that the crowd workers may connect to the access points several times a day regularly. We aim to find a pattern of their incoming and outgoing timings, and based on the information, we predict the chance of each crowd worker being available up to a certain duration from any given point of time. This knowledge can be used before scheduling a job to a crowd worker to avoid unnecessary job loss or job handover, because the job would be assigned only if the crowd worker is supposed to be available until the job is finished, if it was submitted. So the contributions of the research paper, or the novelty that we have produced in this research paper, are to predict the availability of crowd workers. We opted the following steps. Based on the historical data, a deep learning based prediction model is presented to predict each SMD's stability within a particular network, that is Wi-Fi access points, at a given point of time. And we have used conv-LSTM API in Keras that utilizes a convolution layer for feature extraction and LSTM for prediction. Number C, the session timeout of a SMD is predicted for a given session in time, and a random job submission system is simulated to evaluate the performance of the prediction model using various metrics. So crowd worker availability prediction. The Crowdworker availability is predicted based on the user's history and is a classical problem of time series data prediction. The architecture of the proposed method is highlighted in the figure number 1, as you can see on the screen right now. And to solve the Crowdworker availability selection problem, we identified 5 main pipeline stages as discussed in the following slides. So you can see that we have the start when we go for data collection, and after the data collection we go for data pre-processing, in which we perform data filtering and data sampling, and after pre-processing we go for feature extraction, and then we have the prediction model that is using conv LSTM 2D. After that we go for Crowdworker selection, and that's the end of the architecture. So under data collection, for gathering the data, a logger program is developed using Python 3.6 environment, and the program script is developed as a service which continuously looks in the WLAN for the devices connected to Wi-Fi access point. So the complete procedure is as follows: that the Wi-Fi access point at Data Engineering Lab of NIT Durgapur is selected. The Python script continuously monitors the wireless network interfaces. All the devices connected to the access points are identified using their MAC addresses. Login is skipped for other devices connected than SMDs by filtering the MAC addresses, and the SMDs are logged by the program identified their MAC addresses and the session in time and out time. These 3 parameters are logged and stored into local MySQL database for further analysis. So now we discuss the data collection, in which the generated data set which we have collected from the Wi-Fi access points can be considered as a univariate data set of the session duration parameter, and the schema of the data set is shown in figure number 2, and you can see on the screen the session duration is the difference between in time and out time for a particular session, and the MAC addresses of the devices are considered as the UIDs. So now we talk about data pre-processing. So data pre-processing, we have performed the following steps. So for data filtering, in this problem the data set has total of 154 users, out of which we selected the top 50 users for the highest number of login activities. This filtering ensures that we considering only the active users as a part of prediction, not the random user who probably logged in a few times. Data sampling, using random sampling method, the data set has been divided into 10 chunks, that is from D1 to D10 of test and train sets with a ratio of 80:20 for training and testing respectively. So for the feature extraction, to improve the model performance, we identify the suitable features from the dataset. In the dataset, all the input variables of numerical type and 3 important methodologies used are scaling, transformation distribution, and identification and removal of linear dependencies between the input variables. We used min-max scaler to scale the data and normalize them, and then we have used quartile transformer for the transformation of distribution, and principal component analysis is performed for removal of linear dependencies. Now for the prediction model, now that's the main step for our research paper. To feed the input data into the conv LSTM model, the data samples are split into sequences where the time steps are the count of the subsequence. The number of steps for 50 total users is selected as 6 for every 2016 data points, and a total of 336 steps for each user. The model expects that the input data shape as a 2D image, hence the input data are reshaped accordingly. Since the session duration is only the feature, the number of features is set to 1. So this is the prediction model continued. So the Keras Python API provides a predefined implementation of conv LSTM module, and the conv LSTM 2D accepts 4 parameters, that is filters, kernel size, activation, input shape to make the data flatten. And all the parameter values are shown in table number 1, and you can see under filters we have the value 64, which is used for capturing the localized data points. Kernel size values 1 and 2, in which the row number is selected as 1 due to univariate nature of data. We have activation, the value is RELU, that is rectified linear unit, that is used for activation data function used in introduction of non-linearity in the data set. And we have the input shape, that is 2131, and sequence is equal to 2, 1. So the steps in designing the conv LSTM prediction modeling are as follows. The sequential Keras model is selected, and the conv LSTM 2D layer is added to parameters as we have discussed in table number 1 in the previous slide. The model output is flattened, converted to single dimension in order to work with LSTM. A single dense layer is introduced as the last output layer with 1 node, and the model is compiled using the default Adam optimizer, and the loss is calculated using the mean square error, that is loss function. So now we have the Crowdworker selection. The criteria for Crowdworker selection is that the predicted availability duration must be greater than job execution duration. For the selection, the confidence of the prediction model is taken into account, and the minimum confidence threshold for selection criteria depends on particular application, that is job execution time, etc. And for the sake of simplicity, in this paper we set the threshold heuristically to 0.74, since the system precision using forecast bias is found to be 0.7371. So test results, we tested the prediction model by assigning the task with various task sizes randomly to the simulator. We recorded the number of tasks in the number of times when a crowd worker departs before completing the assigned task, and the observed performance of the model and evaluation metrics are discussed in the next slides. So you can say this is the test training and testing performance. We measured the accuracy and loss of the model over 10 epochs. The training accuracy versus loss graph and the testing accuracy versus loss graph are shown in figure 2 and figure 3 and figure 4 respectively. The model achieved 82% and 78% training and testing accuracies respectively, and the difference in accuracy and loss between training and testing are only 4 and 7%. So the model evaluation matrices, you can see the experimental results are tabulated in table number 2, and the average accuracy for considered 10 sample data set is 78.43%, and the average prediction error is 21%. And you can see with figure 5, it shows the forecasting error estimates. So in this we can now conclude. So in this paper we built a model based on availability of SMD in a MCC environment, and the model efficiently uses a convolutional layer for feature extraction and LSTM for prediction. The difference between testing and training accuracy is 4%, indicating the induction of sampling phase has been successfully introduced in the dataset. And overall you can say the model has achieved an accuracy of 78.43, which is quite good, and hence we can conclude that the proposed prediction model is able to predict the availability of SMDs in local MCC in a satisfactory manner. However, the proposed work can be extended by replacing LSTM with GRU and using hybrid prediction models. So if you have any questions, please email us at anandnayyar@dutan.edu.vn. Any queries will be responded in less than 24 hours. And thank you so much for inviting us. Thank you so much for listening.
Hello everyone, my name is Sayan Roy. Hope you people are doing good in this current COVID situation. Today, me and my co-researcher Binoy Sasman would be discussing about our paper, Integration of Hierarchical Clustering and Dendrogram Method with Expectation Maximization for Identification of the Best Player Cluster.
Let's get started with the introduction part. As more and more computer power become available in the past decades, computing statistics using large amount of data become more mainstream. This rise influenced the use of data science within the field of artificial intelligence as one of the strategies in optimizing data variables. Over the past years, we also see more and more machine learning techniques have been applied to sports data. Clubs started analyzing their players using statistics and using machine learning techniques to maximize player performance, and sports data analysis can vastly improve team performance and help coaches make the right decision. In this paper, we have compared two machine learning clustering techniques on football data, hierarchical clustering and expectation maximization. We will determine which technique cluster the data best using two cluster evaluation method, purity and the silhouette score. Next to that, we will calculate the best cluster size and see the best way to separate the data. At last, we will determine the best and worst features in our data for these clusters using the silhouette score, Laplacian score and the correlation mean. Coming to related works, previous work within the field of football analysis dominantly contains paper with supervised learning methods. In Decruz's work, individual players are analyzed using similar event dataset in comparison to our to determine the overall strategy the coach imposes on the team. Instead of single events, it calculates event streams and deduces phases during a football game. Work by Liu et al. Focuses on classifying players from a video stream of the match. It also uses expectation maximization clustering. Liu uses expectation maximization on different types of player images and overcome the problem that in dataset not every player cluster has the same size. Study by Mahfouz et al. Focused on unsupervised learning techniques used in this paper. Mahfouz primarily used k-means and expectation maximization to do overall analysis of the player performance. The analysis was focused on the training data and drills, did not include any matches. Study, however, fails to draw any notable conclusion. Overall, we can conclude that related work is dominantly based on supervised learning. This thesis will fill gap here and contribute the research on applying unsupervised learning techniques on event data of football matches. Now coming to dataset part, we use two different dataset in our research. One is StatsBomb and the other is FIFA dataset. StatsBomb contain a sample of 809 matches, all of which from the Spanish football competition La Liga. For each match, it defines what sort of event happened in a match, such as passes, shots and dribbles. From 809 matches, we used 452 matches. In those 452 matches, 1.6 million events have happened, on average 3,559 per match. We again cleaned the data such that the column we are using in the end consists of player, position, location, type and related events. The FIFA data originates from the EA Sports game FIFA 19 containing 89 columns, 80,206 rows with players and their attribute score. We analyzed way in how we could correlate both data to discover what insights we could receive. Methodology. In total, we have used two unsupervised clustering methods, namely hierarchical clustering and Gaussian expectation maximization. We also used principal component analysis for visualizing the data. At last, we used four scoring methods for evaluating purposes: purity, silhouette score, Laplacian score and correlation mean. We use purity for knowing how good a cluster performs and uses the actual levels to calculate the correlation between the predicted and actual levels. We use silhouette analysis for predicting best algorithm as well as calculating the best cluster size. Silhouette analysis calculates how similar data is to data in their cluster in comparison to data in other clusters. Continuing to slide 6, we use PCA to visualize the data from 23 dimension into 2 dimension to plot it in a scatter plot. To verify the results of column and feature selection we have done with the silhouette score, we use a method that focuses on identifying good and bad feature in unsupervised data, named Laplacian score. Laplacian scores score features based on how they preserve each cluster. They seek which features are best in containing two closed data points close. Laplacian score use a graph where nodes are data points and edges of each node are its nearest 5 neighbors. Based on the Euclidean distance between the two, we define a weight matrix based on this graph measuring similarity between each neighbor if two nodes are connected.
The data we analyzed is 25 dimensional. To visualize this data, we used PCA to reduce the dimensionality to 2 dimensions. For the first clustering task, we set the number of clusters to 4. The number 4 corresponds to the different groups of positions in the football field, namely the position of goalkeeper, defender, midfielder, and forward. In the figure, we can see that the data clusters do overlap, except for the goalkeepers. An exception for this is that goalkeepers tend to stay in one location and tend to have quite different action in comparison to the other players on the field. In these figures, we can see hierarchical clustering and expectation maximization algorithms. In both methods, we used 4 clusters as we tried to model the cluster of the 4 positions on the field. We trained both methods on all the data with 30,000 iterations. We see that the hierarchical clustering algorithm tends to keep the cluster size the same. The expectation maximization algorithm, however, tends to cluster most of the data in one group. According to the purity score, we can see that hierarchical clustering does a better job at classifying the right cluster in comparison to expectation maximization. However, the silhouette score is close to 0 and suggests it might be better to take different number of clusters. Next up, we use a higher number of clustering, which is 11. This number of clustering corresponds to the number of positions of players on the field. We trained the model on data and again used 30,000 iterations. We visualized the data in 2-dimensional using PCA first, as shown in the figure. We see that there is almost no separable data except for the goalkeeper, which again do have their cluster. In these figures, we can see hierarchical clustering and expectation maximization algorithm with 11 clusters. We can see that expectation maximization tend to cluster the data somewhat better than with 4 clusters. Next to that, we again see in expectation maximization that some clusters are way more extensive than others. Both the purity and silhouette scores are in all cases way worse than using only 4 clusters. We we can see that individual players' positions are not clusterable at all. The data does not differ enough between the different clusters to separate the player into position categories. We now know that hierarchical clustering is better algorithm. We also know that 4 clusters work better than 11 clusters. For every number of clusters, we train the model and calculate the silhouette scores. We see that cluster size of 8 has the highest silhouette score, meaning 8 clusters do create the best cluster where each cluster is most apart from other clusters. The main finding of this study were that the amount of 8 clusters best separate player types. With the use of silhouette analysis and hierarchical clustering, we saw that all other cluster sizes scored worse separability of different type of players. From this, we can say that given a football match, we classify each player performance as either one of 8 types. Thus, there are only 8 types of players in a football game. In contrast to 11 or 4 player positions, we conclude that some positions within football are redundant or perhaps versatile. From our PCA visualizations, we see that goalkeepers are uniquely defined and do not correlate with other players in the field. We see that the cluster size have about the same size according to the labels. Expectation maximization tend to neglect evenly sized clusters, and this might have influenced why we saw hierarchical clustering outperform expectation maximization. Hierarchical clustering was able to classify 66% of the data correctly when using 4 labels. With the use of feature selection, we see that we can increase the performance of the hierarchical clustering algorithm by 37%. This score indicates that feature selection is essential when fine-tuning a model, whether supervised or unsupervised. Prior studies also tell us the same. The scientific conclusion is that fine-tuning parameters and feature selection plays a significant role in changing machine learning algorithms to adapt to specific problem domains. Thank you.